This video will show you how to use the Process Metallurgy module by walking you through an example representing a simplified steel-making process in a basic oxygen furnace, or BOF for short. The Process Metallurgy module was introduced in Thermocalc 2019B and is a calculator that makes it easy to set up calculations for steel and slag. This example uses a demo database, so all users with a license for Thermocalc 2019B or newer can follow along on their computer, even if you do not have a license for the Process Metallurgy module. This video is based on example PMET-01, Basic Oxygen Furnace, which can be accessed from within your software in the Help menu, Examples Files, Process Metallurgy. To begin, click on the Process Metallurgy template from the home screen of Thermocalc. If you have a license for the Process Metallurgy module, the program will automatically select the highest version of Oxide database that you have, back to TC-OX8. This example works with all TC Oxide databases, including the free OX demo database, so users who do not have a license for a TC-OX database can still run the example. I will use the free OX demo database, so select that from the drop-down menu. Set the temperature to 1,650 degrees Celsius. In Thermocalc 2019B, the Process Metallurgy module only allows for isothermal calculations. The possibility to run adiabatic calculations will be added in a coming release. It will then be possible to calculate the temperature increase in the BOF due to the exothermal oxidation reaction taking place. The center of the Process Metallurgy module contains the materials, which are divided into three groups. Most steel processing methods involve liquid steel, liquid slag, and a gas phase. So the module makes it easy to define the compositions of a steel and slag system by offering materials groups for each of these. One group for steel, one group for slag, and one group for gas. Each group offers different default input types that are relevant to that material group, which we can see if we click Show Composition next to each of the materials. The default input type for the steel group is element. For slag, it is component, and for gas, it is gas component. You can add additional materials to each group by clicking the green plus sign above that group. The new material inherits the default settings of that group. We do not need any additional materials, so I will delete the material I just added. Let's set up our steel. We will accept the default unit as ton and set the amount to 100 tons. The composition for each material is hidden because the module allows you to easily save materials and access them from the Material drop-down menu. So once you save a collection of materials, you will rarely have to click Show Composition. This is our first material, so we will select User Defined from the Material drop-down menu and then click Show Composition so we can set the composition for our steel. We will accept all of the defaults for the input type. Next, we will add the elements. We will leave the first element as iron, which is the default. Click the green plus sign next to Major Components to add another element. Set it to carbon with 4.5 weight%. Click the green plus sign again and set the third element to silicon with 1 weight%. This automatically sets iron to 94.5 weight%. We are now done defining the composition of the hot metal in the BOF, so we will save the material so we can use it in the future. Click the Save Material button. Name the material Steel_BOF or whatever name you prefer, then click OK. The material appears in the drop-down menu immediately and will be there every time you open the module. The Process Metallurgy module automatically saves your material in the relevant material group. So only steel materials are shown in the steel drop-down menu, only slag materials are shown in the slag drop-down menu, and only gas in the gas menu. You can delete materials and make other changes to the Process Metallurgy module by going to Tools, Options, Graphical Mode, Process Metallurgy Calculator. You can also create additional materials groups if there are groups you will use regularly, such as scrap compositions, ferroalloys, or slag additions you regularly use in your company. We are now done with the steel, so I will hide the composition to keep the screen clear. Remember, you could add another steel if, for instance, you wanted to define a composition of a steel scrap to add to the BOF. This example only has one steel, so we will move on to the slag. Again, we will leave the material as user-defined because we will set it ourselves. Change the unit to kilogram and enter the amount as 3,000. Click Show Composition, then click the green plus sign once to add a second component. Leave the first component as calcium oxide. Set the second component as aluminum oxide with a composition of 25%. This automatically sets the calcium oxide to 75%. Again, click Save the Material, name the material Slag BOF, and select OK. Notice that the material is now listed by the name you just saved. If you click on the drop-down menu under Grid Definitions, you will see that the materials are listed by the names we gave them, followed by the material group in parentheses. If you do not name your materials, they will be listed as user-defined and material group, which can be confusing, so we recommend you always name your materials. Again, you could define more sets of the slag group and save them for future use by clicking the green plus sign above the slag group. Finally, we will input 1 ton of the gas phase. The composition of the gas is pure oxygen, so click Show Composition and make sure that this is selected. Click Save Material, name the material Oxygen, then click OK. This completes our definition of the calculation conditions, so we can move on to the calculation type. For more complex calculations, it is good practice to start with a single equilibrium calculation to make sure the calculation converges. Also note the Options tab, which can help if your calculation fails. Our calculation is simple, so we will select a one-axis calculation type. The drop-down menu displays all the stepping options we set above for steel, slag, and gas. Select Amount of Oxygen and set the limits from 0 to 10 tons, and increase the number of steps to 40 to have a finer resolution. The calculation is now set, so click Perform Tree at the bottom center of the program. Once your calculation is complete, your plot will appear in the results pane. By default, the amount of phase group as a function of amount of gas is plotted. The concept of phase group is new and was introduced for the Process Metallurgy module to make the interpretation of your results easier. Phases of similar type are bundled together in the groups liquid metal, solid oxide, liquid oxide, and gas. All the groups except the gas phase can have more than one phase. This grouping is particularly useful for liquid metal and liquid oxide because they are both described by the same phase, ionic_liquid, and because there will typically be 2 or more composition sets of ionic liquid. This is also useful for solid oxides because a large number of phases can be stable, making the interpretation of results difficult without this grouping. Zooming into the low gas amount, it can be seen that the evolution of the gas phase is retarded. The reason is that the oxygen gas first oxidizes some of the silicon dissolved in the steel to form silicon dioxide. Only when the silicon content in the steel has dropped below a certain level can the oxygen gas burn away the carbon dissolved in the steel to form a carbon monoxide-rich gas phase. These reactions can be investigated in more detail with different plots, so we will do that. Right-click on the Process Metallurgy Calculator node, highlight Create New Successor, and select Plot Renderer. For the y-axis, select Composition of a phase group, liquid metal, and all elements. Then click Perform again. The reduction of the carbon content can be clearly seen in this plot. This reduction of the carbon content is what is termed steel making. The hot metal coming from the blast furnace has a very high carbon content of typically 4.5 weight%. If it is left to solidify without lowering the carbon content, it will be extremely brittle and be unfit for rolling or forging. Other changes in steel chemistry occurring in the BOF can be made visible by changing the y-axis type from linear to logarithmic. So we will do this. In the Axis Type drop-down menu, select logarithmic 10, then click Perform again to plot the steel chemistry as a function of amount of oxygen added in logarithmic scale. Now we can see the removal of the elements from the liquid steel in the following order. First calcium, then aluminum, then silicon, and finally carbon, according to their position on the Ellingham diagram. Finally, we will create one last plot. So right-click on the Process Metallurgy calculator, highlight Create New Successor, and choose Plot Renderer. Set the y-axis to Composition of Phase Group, Liquid Oxides, All Components. Then select Perform again. This plot shows how the liquid slag composition changes as a function of the amount of oxygen added to the BOF. At first, the silicon dioxide content of the slag rises sharply. This is due to the initial oxidation of the silicon dissolve in the hot metal. The silicon dioxide that is formed combines with the slag and increases its silicon dioxide content. This increased silicon dioxide content reduces the liquidus temperature of the slag and thereby, as we can see in the first plot we made, increases the amount of liquid slag and reduces the amount of solid oxides. This is also exactly what happens in reality. On further addition of oxygen to the liquid steel, the silicon dioxide content in the slag increases further and further as more silicon is oxidized and combines with the slag. At the same time, the oxygen partial pressure in the steel slowly increases. After about 6 tons of oxygen have been added to the system, the oxygen pressure is high enough to start oxidizing the steel itself. The slag quickly becomes rich in iron oxide. When this starts happening, the steel-making process is complete and the steel is ready to be tapped into a ladle for further steel refining. To learn more about the Process Metallurgy module, watch the additional videos by clicking the links currently on your screen or visiting our website at www.thermocalc.com.